Okay, as promised, we're going to up our game. We were able to deal with two equations in two variables pretty well. What happens when we have three equations in three variables? Well, the book describes this as the intersection of three lines in a three-dimensional plane. I will not get into the particulars here in this video. I'm just going to go through the method of solving this. However, you are advised to read over your section, and especially the background given on pages 274 and 275 of your textbook. So pages 274 through 275 gives an excellent reading on what we're actually doing right here. And you might want to just take a moment before you get too far into this to get an idea of what it is they're doing. Okay, so I have three equations, and they contain three variables each. How can we possibly find a solution of the form, when we say an ordered triple, we want a solution of the form x, comma, y, comma, z. We want a three-piece coordinate, I guess we could call it, an ordered triple. Well, the key here is that in order to do that, we can take two equations at a time and whittle it down. That is, to find a way to get rid of one of the variables in one of the equations and then use that same equation to get rid of the same variable in the third equation. So we're going to use line 1. So I always consider my first equation as my reference equation. And I ask myself, if I take my first equation, what could I do to get rid of one of the variables in equation number 2, let's say? Well, let's look this over. We've got 2x and x. We've got negative y plus y, 4z plus 2z, and 7 and 2. Well, it looks like right away, if I were to add equation 1 and equation 2, y would drop right out. So let's write that down. Let's take line 1 and just directly add line 2. Right? I just label this off to the side. Let's see, what does that look like? Well, 2x minus y, that's not a y-ish looking y here. Here's a minus y plus 4z will equal 7. And line 2 says take x plus y plus 2z, and we get 2. And when we add these two together, we get 3x, we get 0 y's, and we get 6z. And that will equal 9. So now we have an equation with two variables in it. Interesting, you say, but okay, now what? Well, since line 1 is our reference equation, we use line 1 to get rid of y in equation 2, then we must use line 1 to get rid of y in equation 3. That's why I call it my reference equation. If line 1 is my reference equation, I'm going to take line 1 and use it to get rid of the same variable in lines 2 and line 3. So, question. If we took line 1 and we wanted to get rid of the variable y in line 3, what would we have to do? That's right, we're going to take this equation and multiply it by 2 on both sides. So in other words, now we're going to go with 2 times everything in line 1 and add that to line 3. And our objective here is to get rid of the y variable when we do that. So let's try that out. Let's take 2 times everything in line 2, right? In line 1, pardon me. So 2 times 2x minus y plus 4z, and set that equal to 2 times 7. That's going to give us 4x minus 2y plus 8z equals 14. right? And we want to add that to line 3. So let's just take our line 3 as is. We've got x plus 2y minus 2z, and that is equal to negative 1. And if we add these two guys together, 4x plus x gives us 5x. The y term drops out. Plus 6z is equal to 13. All right, you say, well, that's well and good, Professor Peoples, but now what? Now, look at what we just made. We've got a new equation that we just formed by adding a variation of line 1 and line 2 together. So we've got 3x plus 6z equals 9, an equation in 2 variables. And we've got 5x plus 6z equals 13. Would you know what to do if I gave you that as a system of equations? Absolutely you would. You would take this system of equations. I'm going to change my color here. If we call this equation 1 now, and if we call this equation 2, we could take these two equations and somehow get rid of one of the variables by the addition method. And in this case specifically, let's try taking the negative of equation 1 and adding that to equation 2. Right, so that's going to be our next job right here. Let's take the negative of every term in the first equation. That gives us negative 3x, negative 6z equals negative 9. And we're going to add that to 5x plus 6z equals 13. And when we add together here, we're going to get 2x is equal to 13 minus 9, that's 4. And dividing both sides by 2 isolates x altogether, giving us x equals 2. All right, so we know that in our ordered triple, we're going to get 2 as our first coordinate. We still don't know y and z, right? So how do we get those? Well, now we back substitute into the two equations that we just got to solve for z. The other variable that we didn't drop out the first time we did all of this. So let's try one of those two equations. Let's put in 2 for x into the first equation. Let's see what happens. Let's put 3 times 2 plus 6 times z should equal 9. Well, this is to say 6 plus 6z is equal to 9. And so doing the subtraction here of 6 from both sides, we end up with 6z is equal to 3. And so we end up with z is equal to 1/2. Interesting, interesting. Okay, z is equal to 1/2. So we've got the third piece of our ordered triple. All right, let's try one more here. What happens if we put in z equals 1/2? How are we going to get y? Well, we dropped y out of the first equation, so let's go back to our original equation again. This time back substitute again, putting in 2 for x, so 2 times 2, minus y, plus 4 times z, which we now know to be 1/2. Set that equal to 7, and let's solve it. Now, we could have picked any one of the three original equations, whichever one was most convenient. This is going to turn into 4 minus y plus 2 equals 7, which is to say 6 minus y is equal to 7. So I'm going to have to subtract 6 from both sides to get negative y is equal to 1, which means that y would have to equal negative 1 to make this true. And so our ordered triple is 2 negative 1 1/2 in this example.